Hello and welcome back to another video. So in this video we're going to study about thin lenses, which is an important part for IGCSE Physics. Let's start. As you may know, we have two types of lenses. We have a converging lens and we have a diverging lens. Remember, converging lens is also called as a convex lens, okay? So what this basically does is that when you have a parallel beam of light, for example, the beam of light is coming and falling on your lens. This lens is going to converge it at one point, something like this. On the other hand, a diverging lens is going to diverge your light beams, okay? And they have different purposes in our practical lives, which we'll go through it one by one. Now, let's discuss some important features, important parts of a thin converging lens. Let's start with this is your lens, okay? And this has an optical center. Optical center, or C, is basically the center of your lens. Now, what is principal axis? It's basically a perpendicular line that passes straight through the optical center. So this is something like this. This is a principal axis. Now, what is principal focus? Principal focus is the point on the principal axis on which refracted beam of light meet, okay? So each lens has its own focal point, and they will tell you, for example, if it's 2 centimeter, okay? So you have to measure from here, from your optical center, you're going to measure 2 centimeters, okay? So this is, let's say this is 2 centimeter, you will call it F, and then you will measure another 2 centimeter. This is going to be 2F, okay? This is F, again 2 centimeter on the left, and another 4 centimeters. That is going to be 2F, okay? 2 centimeters plus 2 centimeters. So this is basically your focal point. Now when your light beams are falling, this is where they are going to meet in a converging lens, okay? So you will draw a line here. When your beams are falling on this lens, they are going to converge and pass through the principal axis by moving through the focal point, okay? Let's draw the arrow, something like this, because now let's draw another beam of light. Another parallel beam of light is coming and hitting the lens, and it's going to converge, right? Because it's a converging light. Again, it's going to pass through the focal point, like that. Next, focal length is the distance between the optical center and the principal focus, okay? This one. You have an object which is kept 3 centimeter in front of a convex length, and the focal length is 2 centimeter. Find out the position and the nature of the image, okay? So let's start with the focal length. You need to draw your focal points, which are 2 centimeter from the optical center, okay? Let's do that. So use a ruler, F and F, and then you're going to draw 2F as well, which is 2 centimeter plus 2 centimeter, 4 centimeters from the optical center. So approximately here. Now, the object is placed 3 centimeter in front of the convex lens. So if this is 2 centimeter, 3 centimeter is around here in the center. Remember, notice it is between F and 2F, okay? So draw your object here. Object is just an arrow. You can label this as O. So now when you want to find out the nature of the image or the position, the first step is you have to draw a line from the top that passes straight through the optical center, okay? Now you have to draw another ray, okay? Draw this ray parallel to the principal axis, and then it's supposed to cross through the focal point, exactly like this. And at the point at which both of these rays are intersecting is where your image forms. Now there's also another way that you can draw your ray, which is like this. It crosses through the first focal point, and then it's parallel on the right side of the lens. The points at which these rays are intersecting is where your image is forming. But 2 rays are generally enough. You don't have to draw the third one. What is the nature of the image and the position of the image? So you can say this image is further away from the lens. This was 3 centimeter. This is much greater than 3 centimeters. So the image is further away from lens. Secondly, you can see image is larger than the object, right? Also, it's real. Both light rays are actually meeting. And then you can notice that it is inverted, okay? As you can see here the focal length is 3 centimeters, so I have placed focal length at 3 centimeter mark, and then the object is at 7 centimeter over here. Use a ruler to identify where your image is going to be. These light rays are meeting at this point, so the image is going to fall here. The image is smaller than the object. So we're talking about the image here, okay? The image is smaller, the image is inverted, and also it's closer to the lens, okay? Previously it was further away from the lens. So in this next example, the focal length is 5 centimeters and the object is at 10 centimeters. That means it's exactly at 2f. As you can look in the diagram below, you will see that the object is also at 2f. The image is therefore inverted. It's the same size as the object and it's also equidistant from the lens. Both the object and the image are at the same distance from the lens, and it's real as well. Okay, now let's move on to another example. Here the focal length is 8 centimeters, but the object is at 2 centimeters. That means the object is between f and the optical center. So that means it's very close to the lens, and let's draw the ray diagrams and see what's happening. The first ray passes straight through the optical center, and you'll draw the second ray which is parallel to the principal axis, and then it passes through the focal point. But if you notice this, that these rays are not intersecting, they're just diverging away and away from each other. So if they're not meeting, we're not getting an image over there. So what do we do is that we are going to extend the lines backward, and at the point where both of these lines are intersecting is where your image is going to be. Now such an image that forms where light rays do not actually meet but they appear to meet, as in here, this is a virtual image, okay? Also the image is larger, so this is used in magnifying glasses, and this is upright. Also this is the image is formed behind the lens, behind the object. Another point to note is that you have to keep position your eye in this place to able to view that magnified image, okay? So over here I have summarized the rules that you need to know about where the image is formed, whether it's real or not, what's the size. If you want, you can take a screenshot and it's going to help you. Okay, moving on. So in this part, we'll discuss how converging and diverging lens are going to solve or correct our eye problems such as long-sightedness and short-sightedness. Now, long-sightedness is basically when you can see objects that are further apart from you, but you cannot see objects which are close to you, okay? So the problem in, remember, converging lenses are also called as convex lens. So the problem basically is that the lenses of your eye, which are naturally present in our eyes, they focus light behind the retina and not on the retina. So when the light is not focused on the retina, image, we get a blurry image. Must be on the retina. That means the light rays must intersect on the retina. So as you can see here, this green is the converging lens. It's going to converge the light before it enters your eye. So it has moved the focal point backward, and now the light rays are focused on the retina and you're getting a very clear and focused image. Now we'll see how short-sightedness, which is when people can only see objects that are near them, can be corrected using a diverging or concave lens. A lot of people suffer short-sightedness as they age, okay, because their lens become weaker. Now the problem here is that the lenses of your eyes are focusing light in front of the retina, not on the retina, and that's why you get a very blurry image. So a concave lens, which is basically a diverging lens, is going to diverge the light before it enters your eye. This is going to move the focal point backwards, so the light rays are focused on the retina. This figure presents an object O placed in front of the converging lens. This is object O over here. State the full description of the image I. Okay, so you can see that this image is larger than the object. It's upright. Both of the arrows of the object as well as the image are pointing upwards, and this image is virtual. The lines are not actually meeting together, right? It's just that they appear to meet. So this is a virtual image. Then use letters on figure 7.1 to identify the focal length of the lens. Focal length is the distance from the optical center to the focal point. This is focal point because when you're drawing your rays, you have to draw it perpendicular, or sorry, parallel to the principal axis, and then it goes straight through the focal point, RS. On figure 7.1, draw an eye suitably placed to view the image eye. Okay. Next, figure 7.2 shows an object O placed to the left of the converging lens. A principal focus is marked at this position. On figure 7.2, draw two rays to locate the image of the object O. You can use a ruler. Make sure that you're using a ruler and draw a line straight through it. You will take your ruler and draw a line that is parallel to the principal axis. And then this should go straight through the focal point. Inverted, as you can see. Now on figure 7.2, draw one more ray from the upper tip of the object. We have drawn two rays. Now there's another way to draw the ray, and that is you need another focal point. So this is your focal point. Use a ruler to mark another, something like this. So this is the other focal point. Now you're going to take a ruler and draw another ray that goes from the tip of the object and passes straight through the focal point, okay, like this. On the right side, it will be like this. This is a third way. On the figure, a convex lens is used to produce an image of the object. Place 3 text that describes the image. Can only be formed on the screen. No, because this is only for real images, okay? As you can see over here, this is a virtual image because the lines are not actually meeting. So it's not this. Diminish, that's not correct. Enlarge, yes, the image is enlarged. Inverted, no, it's upright. It's not real. You only need to mark the ticks, not crosses, so remove that. Same size, no. Upright, yes, it is, and virtual as well. On figure 7.1, mark E to indicate the possible position for eye to be placed. And then state an application in which a convex lens is used. In this way, that is going to be magnifying glass.